Hi, everybody. Welcome to our session about Kubernetes and SUSE Manager and how they can work well together. I'm Flavio Castelli, and today with me there is also Michele Bologna working on SUSE Manager, while
Hi, everyone.
While I work on SUSE CaaS Platform. So the agenda for today is to talk a bit about Kubernetes, how a cluster of Kubernetes is made, what is it made of, what are the challenges that we face when dealing with upgrades of a Kubernetes cluster. Then we will look at SUSE CaaS Platform and how SUSE is helping you to solve these challenges. And then we will switch to SUSE Manager, another project from SUSE, and Michele will talk about how SUSE Manager can not just help you manage traditional machines, but also how it can help managing Kubernetes clusters. So without further ado, let's start with some basic concepts. So Kubernetes clusters are made by basically three kinds of nodes. You have control planes nodes, also called master nodes, and these are the nodes where the Kubernetes server components are running. Components like the API server, the scheduler, controller manager, they are running on the control plane nodes. Then you have etcd nodes. etcd is database, is a key value store used by Kubernetes to store all the information about the cluster, meaning all the workloads that are running on top of it, all the configuration that you provided for these workloads. Everything is stored inside of etcd. It's really important to have etcd available and reachable all the time. And then finally, we have worker nodes, which are the nodes where your workloads are actually running. All the containers that you want Kubernetes to run are scheduled and are executed on top of the worker nodes. Most of the times, we have two roles conflating together. We have the control plane nodes and the etcd nodes that are basically the same node. So this kind of simplifies things from a certain point of view, but that's not enough, because running Kubernetes poses some challenges. So first of all, when you have a Kubernetes cluster running in production, you always want to have an odd number of etcd nodes. That's because etcd requires an odd number of nodes in order to be resilient to sudden failures of the nodes. The odd numbers comes from how the protocol used by etcd works in order to reach the consensus, to reach the quorum among the different members of an etcd cluster. And given what I said just before, that etcd nodes are most of the times also are placed on the control plane nodes, you always end up having at least 3 control plane nodes. So this is minimum if you want to go in production with Kubernetes. And when it comes to handle the upgrades of all the machines, so control plane nodes, worker nodes, you can't handle them like traditional Linux machines. You can just go apply some updates and then reboot the node. You can't do that because there are many risks of breaking up your Kubernetes cluster. So for example, if you reboot too many etcd nodes at the same time, you are at risk of breaking the quorum algorithm of etcd. And if that happens, etcd becomes read-only, and you can't interact with it from Kubernetes, and your whole Kubernetes cluster becomes not really useful to you. And on the other end, if you upgrade too many worker nodes, you might basically cause yourself a DOS attack, because as soon as you reboot a node, all the workloads that were scheduled on this node are automatically restarted by Kubernetes somewhere else inside of the cluster. And if you reboot too many worker nodes at the same time, you might end up running too many workloads on a limited number of worker nodes, and these worker nodes are going to become overloaded, and some workloads will get killed because of that, or others will become unschedulable because there is no more space left inside your cluster. So you can end up causing serious downtime to your own cluster. At the same time, There are also cases where just rebooting a worker node can cause some issues to end users of a cluster. So for example, a lot of users are also starting to run long-running processes on top of Kubernetes, like machine learning computations. And if you reboot one of these machines, then this workload is going to be restarted from scratch on another machine instead of a cluster. And so the data scientists waiting for the result of this machine learning training or whatsoever will have to wait more time. Some users want to avoid that and want to have a mechanism in place to notify the administrator of a Kubernetes cluster that important workloads are running on a node, and hence the node should not be rebooted until these workloads are done. So how can we solve all these problems? Well, SUSE has a Kubernetes distribution called SUSE CaaS Platform, which aims to solve these challenges on top of providing you a fully supported Kubernetes distribution that goes from down the kernel, which is where all the containers features live. So containers are made of kernel features. So we support them down to the kernel, thanks to our deep knowledge of the Linux kernel, up to the Kubernetes stack and beyond the Kubernetes orchestrator, because Kubernetes is just a platform on top of which you're going to deploy a lot of other workloads and a lot of other add-ons for it. So SUSE CaaS Platform is made by basically two kind of items. You have software that is shipped in a, let's say, traditional way, so shipped as system packages, RPMs, and this could be packages that are completely unrelated from Kubernetes, like SSH daemon, the Linux kernel, some system services. And then you have some packages that are deeply related with Kubernetes, like kubelet or CRI-O, which is the container runtime that we use inside of SUSE CaaS Platform. Other than software delivered as system packages, we also have quite some software running in a containerized fashion, which means that on top of our platform, we also have some containers running that are used by the platform. There are some core pieces of the whole platform that are delivered in such a way. For example, the entire control plane of Kubernetes is shipped as containers. So the components that I mentioned before, the API server, the scheduler, the controller manager, they are containers running on top of CaaS Platform. The same applies to etcd, which is running in a containerized fashion. And on top of that, we also have some, we call them core add-ons, which are add-ons that are really important. Without them, the cluster would not be useful. This kind of add-ons are pieces like the network driver of Kubernetes, so the CNI driver that we use, in our case, Cilium. And then we have other add-ons like, for example, DAX Gangway for authentication authorization, and we have many others. So how do we keep all of that up to date in an easy fashion for you? So the system packages, so the RPMs, are managed through a service that is running on each node. This service is called Scuba Update, and this is looking for the availability of non-interactive patches. So these are patches that can be applied to a system without causing a downtime of the service that this patch is going to fix. In some cases, these patches, however, lead to the installation of an update that, in order to be available, in order to be effective, requires the node to reboot. So, for example, if there is a security issue inside of the kernel, then you have to reboot your machine in order to boot with a new kernel. And the same applies to other kind of packages. So what can we do in these cases? Well, in these cases, Scuba Update will identify this kind of upgrades, and we'll create a special text file on the node. This text file is used to signal that the machine needs to be rebooted in order to have the updates in place. And this text file is monitored by a containerized workload that is called Cured, which is running on top of each node of the cluster. this workload, this program is looking for this file, and whenever it finds one of these files, it will schedule a reboot of a node. But it will do that by looking at the state of the entire cluster, meaning that it will make sure that you don't reboot too many nodes running etcd, or that you do not reboot too many nodes that are control planes nodes, assuming that etcd is somewhere else, or that you're not rebooting too many worker nodes. And as I was mentioning also in the beginning, it can also be instructed by the end users of a platform, so that if there is a long-running computation on a node, then Cured will wait for the reboot. It will wait for this computation to be done, and then it will reboot the node, making sure that it doesn't break the whole cluster. But this is just one tiny portion of it. So this is just for RPMs. So what can we do for containerized workloads? Where if you ever used a SUSE CaaS Platform, you will be familiar with Scuba, which is a command line tool that we created to simplify the creation of a Kubernetes cluster, and to simplify some operations like adding or removing nodes, and also simplify operations like updating Kubernetes version, which involves a mix of updating system packages like kubelet or cryo, as I was mentioning before, and updating at the same time also some containerized workloads like the full control plane. And on top of that, Scuba also helps you to update the add-ons I was mentioning before, so CNI drivers and other add-ons like Cured or DAX Gangway and so on. So everything is working fine, but Scuba Updater and Scuba are consuming packages and images straight from the source of them, which is a SUSE Customer Center with its repositories, or if you're using SMT and RMT, it's using what you have mirrored. But are you always fine having these unattended updates consuming packages straight from our repos? I guess that a lot of you are used to manage updates in a more controlled fashion, monitoring what gets rolled out to which system and when. So for all of that, I will leave the stage to Michele, who is going to talk about SUSE Manager and how it can help with this kind of challenges.
Thank you, Flavio. And what I'm going to talk to you about is SUSE Manager. As Flavio said, is another product that we have at SUSE. And what is basically SUSE Manager? So we have here what we call the magic wheel of SUSE Manager, and that is a wheel because SUSE Manager allows you to manage the whole life cycle of your IT infrastructure. So from the health to compliance to security, because SUSE Manager is an open source infrastructure management solution that allows to manage multiple aspects of the IT journey of these days. So for example, we as SUSE Manager can cover the redeployment, the asset management, and the provisioning of the systems. Either they can be either virtualized systems or containers. And speaking of these systems, we are handling package management and patch management with SUSE Manager, and the configuration management with SALT. And finally, we can orchestrate the workload and manage the complexity and the security. So you have your whole infrastructure that can be audited and check the security, check if your systems are vulnerable to a certain CVE audit, and have a report of it in just some clicks. So this magic wheel represents all the features that SUSE Manager allow the users of SUSE Manager to accomplish. But enough with the theory. I'm going to use screenshots of SUSE Manager. So what you can see here is a live SUSE Manager page, and what we want to talk about is the fact that we want to dive down into what SUSE Manager can manage, speaking of Kubernetes clusters. So first of all, Kubernetes cluster can be managed by SUSE Manager, multiple Kubernetes clusters. You can see here I have 2 clusters. I am not very fantasious with names, but in any case, I have 2 clusters, and you can see that both of them are Kubernetes clusters, and those clusters can be managed by SUSE Manager at the same time. So I imagine that, and I know that most of the people, most of our customers out there are using multiple clusters, obviously. So SUSE Manager is, among all the things that I talked before, one solution to manage multiple clusters, Kubernetes clusters in this case that we are talking for this presentation. And what is SUSE Manager capable of? So let's try to dive down into Kubernetes and SUSE Manager. So SUSE Manager first knows the context and the kubeconfig of a specific cluster. So now I'm entering into the scope of one single cluster. And SUSE Manager uses Salt as the configuration management to interact with the Kubernetes cluster underneath the infrastructure. And now I enter the cluster that I selected, and I can see here there are 3 nodes. I can see the host name and various information about my nodes. So the operating system, the CPU architecture, and the memory available. And this is presented in a table. Yeah, this is good, but I want also a graphical way to present it. Yes, I can have that. I can show my cluster in a very graphical way. And to the most attentive of you, have already seen that my cluster is requiring patches because I have 23 security advisories to apply to my system in order to be secure and to be at pace with the current status of security advisory. So tables and a graphical way that not only shows and summarizes the status of my cluster in a graphical way, but I also have precise information and detailed information about patch status, the channels, and some things that we are going to talk in this presentation. Now, I just talked about clusters as objects, but I haven't spoken about single cluster nodes, right? And the idea is to use SUSE Manager as the central management tool for all cluster nodes. And you might ask why, what are the benefits of doing that? So the benefits of using SUSE Manager as a single management tool is that you can reuse the existing policies, the existing software channels, the existing configuration, and the infrastructure management that you already have prepared for all of your infrastructure, for the existing infrastructure that you are running into your data center. So you can reuse all the policies and everything that you have already defined on your clusters because it's already there. It's in a single management tool that you can reuse for everything. And what a notable benefit of this is what we call a GitOps deployment. So given that the infrastructure is laid out and written into a file, it means that you can use that file and version it into a Git repository that represents the evolution and the current status of your infrastructure. Take that file, redeploy your infrastructure from scratch, and have it just like the way you want. Now, those are nice words, and I'm sure that those are really interesting and appealing for everyone. But now let's talk about how these words and the GitOps deployment that we talk about can be implemented with SUSE Manager. First of all, SUSE Manager must know about the nodes that you want to manage with SUSE Manager. So you have to register or bootstrap, that's the term that we use for, to get the system known to SUSE Manager. So you have to bootstrap the system. And what's behind bootstrapping? You have to download a script, so a bash script. You can see here the bootstrap.sh, and you have to execute it, plain and simple. Here I inserted a cloud init example. So you have your cloud instances. You just attach these two commands to your cloud init, and you have magically your system appearing in SUSE Manager. You can see here that after the registration is completed, my tree system showed up in SUSE Manager. And what has the script have done? So the script have downloaded, configured, and started the Salt daemon, which is called Salt Minion, into your system. And this daemon allows SUSE Manager to manage your system directly from the SUSE Manager web or command line interface. Now I have my systems, and let's look at what my system, a single system, is returning. Or I want to look into a single system and what are the details I can look up on this system. So I can see all the information and plus other information that it can fit into a one single slide frame. But the most important information that I can see here is that I have a single pane of glass with the installed product that are running into my node. For example, in this node, I'm running CaaSP, and I can also see other details, especially like the kernel and the IP addresses and stuff like that. So this is just a little bit of information that is shown to my node and collected by SUSE Manager. Now, enough with information. I want to see which is the patch level of my system. So I have single node patching information. I have 3 critical software updates available, and this is clearly shown in the UI for the single node. But let's talk again clusters now. So I want to group my system, my single system, into a production cluster. So I am defining, and SUSE Manager supports that, a system group, so a set of systems that I can group together and have information at the granularity level of a group. So if I define a system group with all my production cluster systems, I can have and see the overall status of my system, like in the second image that we have here, the information for the whole cluster patching information. So I have 24 critical software available for the whole cluster, which is composed by 3 systems. Additionally, since we spoke about GitOps deployment, we are also using Salt. So I'm using an example here that we are using internally. That is, I want to modify the cryo configuration, so the cryo service that runs on top of a CaaSP node. I want to modify its configuration, and I want to be that configuration applied to all the nodes of my cluster. It's plain and simple. With 9 lines of Salt, you can apply this configuration to all of your nodes, and it will, upon a Salt apply, you will get the exact configuration that you wanted as specified in Salt file, and it can be applied to a single node or to all of your cluster nodes. Another feature that our customer already love is the channel lifecycle management. So in a nutshell, what is a channel and what is channel lifecycle management? So as Flavio said, packages and patches come from SCC, SUSE Customer Center, or SMT or RMT. And as soon as you manage a system with SUSE Manager, you have to specify a channel, which is a collection of repositories or channels that define and where your node is fetching packages from. So it's the upstream, let's call it like that, repositories to install packages from your node. And channel lifecycle management allows you to create different channels that are staged for every, let's say that you have 3 environments. So you can create 3-staged channels that you can apply to all of your environments. So how are channels built? You can define the source, which is commonly SUSE Customer Center, and you can apply some filters. And those filters build the fact that you have a state channels with the filters applied. And then you can promote the packages that are in a state channel into the next environment. So for example, if you have development, test, and production environment, you can craft and cherry pick packages and patches for every channel, for every environment that you have. Because, for example, you want to test first your packages and patches before applying to your production environment, and you have different policies in order to promote every package from one environment to the other. But enough with the theory. Let's back to the screenshot. So this is channel lifecycle management in action. You can see here that I have a SUSE Linux Enterprise Server 15 SP1 pool and all the child channels that contains CaaSP, for example. And my filter here is that I do not want the patches that require a reboot for my node. So I'm filtering those patches out, and I'm building my customized channel because my channel will contain only patches that do not require reboot, and I can apply immediately. So this is going to be my state channel using channel lifecycle management, and I want to link to what Flavio just spoke about CASP and Scuba Update. So if you're using Scuba Update, CASP will be automatically patched using the patches that are in the available channels. But if you're using CASP and SUSE Manager to stage your channels, it means that CASP will automatically install the patches that you have defined to install into your CASP node, because you stage the channels and you stage the packages and the patches that you want to automatically install. Finally, what is the additional benefit of running CASP and SUSE Manager? First, SUSE Manager protects CASP nodes so you will not be able to destroy your cluster by issuing some potential destroying operation on a CASP node, for example, rebooting a node. So as soon as SUSE Manager registers a node that has CASP installed, you have a limited set of actions that you cannot issue on that node in order not to destroy your cluster. And one other benefit is that you can join and remove nodes from a cluster using SUSE Manager. So you can grow or shrink your CaaS cluster using SUSE Manager, no more command line. One last thing, the management of a single and a cluster nodes can be enriched with monitoring. So SUSE Manager support the automatic node exporting provisioning for all of your cluster nodes, and the provisioning of Prometheus and Grafana monitoring node for SUSE Manager. What does it mean? It means that for every CASP node, you can have all the data for the system that is running CASP, as well as all the data for the containers that are running inside that CASP node. And that this can be automated, the provisioning of the node exporter and the Prometheus and Grafana monitoring node can be automated using SUSE Manager. Now, if you like this session, please rate it in the survey. You will receive a survey, and our session is the one written here. Please review it. That would be really helpful for us. And we're finished. So I want to thank you, Flavio. And I also wanted to thank everyone for attending this session. I hope you enjoyed. So thank you all for attending, and enjoy SUSECON Digital.
Thanks.